It is my pleasure to welcome Venkat Padmanabhan from Microsoft Research India. Venkat is a senior researcher, done many great things throughout his career, has lots of honors, awards. He's a fellow of every society I can think of. And on a more personal note, I've known Venkat for quite a while. Actually, one of the first papers, for 20 years. So the first paper actually I ever published as a professor was with Venkat and Lily. I don't know if you remember that one.
Oh, yeah, the Infocom one, yeah, done quite well, yeah.
And Venkat was actually my manager when I was doing a sabbatical at MSR India about 10 years ago. But Stefan and I first met Venkat 20 years ago when Stefan and I were still graduate students at the University of Washington. We went to a research retreat at Whistler in Canada. And this is a picture from that time, which sort of shows that all three of us, Venkat, Stefan, myself, we have not changed at all. It's good to know that even after 20 years, we remain ageless. Okay.
Thanks, Jeff, for the very generous and interesting introduction. I must say, in 1998, I was still a grad student for most of that year, so I'm not that old. Okay. It's only towards the end that I joined Microsoft, so okay. Hopefully it will work. No, I think it will work. It should work. Ah, there you go. Oh, sorry.
Sorry about that.
No worries. I will get this back. Yep. Okay. So thank you all for coming. Hopefully you came as much for the talk as for the lunch, so and it'll be worth it. So it's my pleasure to be here. I think I was last here about 10 or 12 years ago, and I think the campus has changed a lot, and it's good to see everyone again. So I'll talk about some work that a bunch of us have been doing on using low-cost technologies with a view to improving road safety. And this is very much ongoing work. We are about a year and a half into this project, and it's work with a bunch of people. And I do want to call out Akshay Nambi, who's a terrific postdoc. Without whom a lot of what I'm going to talk about would not have happened. And there's a bunch of students, others involved. And we're also working with external partners, and I'll talk about some of that later. Maruti RETR, in case you're wondering what that is, we will talk about that later. The motivation for this problem is something that I guess is sadly familiar to all of us. Road safety is a big issue the world over. If you look at the chart on the right from the WHO, it lists road fatalities in the top 10 causes of death. So it's really a public health issue. And in countries like India, it's a particularly acute problem. India actually is among the top in the world in terms of road fatalities because of a bunch of factors. And this is something that is catching the attention of the government, but it's not an easy problem to fix. Everyone knows it's a problem, but it's not something that you can do much about. Now, if you think about it, the factors that potentially impact road safety, the vehicle, the infrastructure, and the driver, all of them really don't see much monitoring today. And I think that's part of the issue. You don't really know, you lay out a road, maybe it's good on day one, and then it develops potholes. You don't really know that. And there's no mechanism to monitor this and sort of take action based on this. And each of these factors is important. I was just looking at just recent news, and I think just in California a couple of days ago, there was a fatality, or actually multiple fatality, which they think is because of perhaps brake failure or some kind of vehicle failure. In Bangalore, where I come from, potholes are notorious for causing accidents, so those are certainly factors. But in our work, we are primarily focusing on the driver because, though all of these factors are important, many studies have pointed to driver or driver-related behaviors and factors being primary causes of safety. So if you look at this report from the WHO, things like speeding and drinking and driving and being distracted and so on are all centered on what the driver's state is, the driver's actions are, right? And that's really what we think is the crux of the problem, and that's what we want to focus on. Now, you might say, okay, if the driver is the problem, why not get rid of the driver? And of course, there's a lot of work happening in this space. Although, as we know from recent weeks, this also is not foolproof. There is issues that could happen. But I think more to the point, there is a huge installed base of vehicles in the developed countries, but also in developing countries like India that simply don't have the capability in terms of sensors, compute, communication, etc. to do self-driving. I mean, you cannot just wish away those vehicles, they are there. And there is of course cost involved in this new technology. And I joke that the only safe self-driving you can do in India is a car that does not move, right? Because the environment is such that you really you have to sort of anticipate the thing that cannot be anticipated in some sense. So it's a tough environment to work in. And so drivers are not going to disappear just yet, and I don't think even in countries like the US, for all the talk, they're going to disappear anytime soon. So I think it is worthwhile focusing on that part of the problem and looking at what you can do to improve safety. So in our project, and because we want to keep costs low and so on, our setup is very simple. We essentially have a smartphone that's on the dashboard or windshield with all of its sensors being used. In particular, we're using the front camera of the phone to look at the driver and the back camera of the phone to look out to the front. We also have an OBD sensor attached to the vehicle generating other data, but really we are focusing on the sensors of the smartphone, in particular the cameras. And I guess the nice thing is that this can be retrofitted onto any vehicle. It's just a question of slapping on a smartphone onto the dashboard. And we have had this set up for more than a year, where we've gathered a bunch of data on about a dozen vehicles at Microsoft Research India, essentially our fleet of cabs. And more recently, we've been working with some external driver training programs on deploying some of this technology in the context of driver training, which also I will talk about. Now, this idea of using a smartphone to measure driving and traffic and so on is not new. I mean, a lot of people have done it. In fact, soon after I moved back to India about 10 or 11 years ago, we did a project called Nericel, which was essentially about a very similar idea, except that our smartphones look like this, not very smart, no sensors. And in fact, even an accelerometer had to be attached externally using Bluetooth. So we did this work in the early days. The paper we wrote actually seems to have done quite well. A lot of people seem to have liked the idea and built on it. And there's obviously commercialization of ideas like this with insurance, telematics, and so on. So given this past work and the commercial activity, the question is, what's missing, right? What existing systems do is largely they gather GPS data and they gather inertial sensor data, right, which tells you things like braking and cornering and things like that. But what I would argue is that what's missing is the driver and driving context. And to illustrate this, let me go back to this old list that I showed from WHO, and let's look at something as simple as speeding, right? You might think, speeding is simple, how fast a vehicle is going, and based on that you can tell whether it's speeding or not. But this is a video of a drive in Bangalore to the airport. So this system is alerting the driver saying, overspeeding alert, please slow down. If you talk to the drivers, they find this extremely irritating because they say, hey, look, there's this whole wide road open in front of me. Everyone's going that fast. Yes, I'm doing 85 or 90 in a 80 stretch, but that's not really, I feel pretty comfortable, right? So the point is that speeding is really to be looked at in a relative sense. How are you doing relative to other vehicle? And we all know this. If you learn driving, you should keep pace with traffic and so on. But a simple GPS-based speeding system does not capture that aspect, right? Likewise, if you look at the internal view, let's say there's a sharp braking that happens. The question is that something that coincided with the driver being distracted? Maybe they were on the phone or looking not where they should be, or maybe there's something sprung up that the driver couldn't have done anything about. Someone jumped in front of the car, or a dog ran across the road or something, right? So you need more context, and we believe that context can be obtained using the cameras, and that's really where that's the delta, if you will, of what we are doing now compared to what we did earlier and what a lot of other work is done. And so as I said earlier, we're using the front camera to get the state of the driver and the back camera to look at the environment in front. Now, obviously, you can do much more detailed monitoring of the driver with variable sensors and steering wheel pressure sensors and all those things. Again, for cost reasons, we are not looking at any of that. We're just confining ourselves to what we can get from the cameras of the smartphone. And with this, we have built a bunch of detectors for the state of the driver in terms of fatigue, in terms of distraction, and what I call as mirror scanning. I'll talk about that later, as well as the driving context. So things like vehicle ranging, which in turn can allow you to detect things like tailgating. I talked about speeding. Also something that's perhaps uniquely Indian, which is wrong side driving. When you have a choice of going 5 kilometers the right way and doing a U-turn and coming back, or going 100 meters the wrong way to get to where you want to, often people make, I guess, the latter choice. and that is obviously very unsafe, but it happens. So it's something that you might, if you're a fleet owner and your driver is doing that, you might want to know that, right? So that's the context. So now, what is the work we have been doing? So I will, there's a lot of moving parts to this project. There's lots of detectors, lots of things we're doing. So I will just sort of call out some broad themes, technical themes, the top 3 boxes, and give you some illustrative examples of work we have done that fit those themes. And then I will talk about some work we're doing with an external partner on deploying this with the driver training context. So broadly, because our system is based on a smartphone, it's retrofitted onto a vehicle and so on, we have to deal with a lot of variation. Simple things like the mounting of the phone could be different. Even in the same vehicle, let's say every day the driver pulls it out and puts the phone back on. The thing could be tilted by a few degrees this way or that way. The vehicle in which a particular phone is mounted could be different. One day it could be in a large SUV, and next day it could be in a small compact car. So the geometry, the configuration of where the driver is sitting and so on would change. So you cannot be training the system afresh every time you do a deployment. I mean, that simply would not fly. So you have to auto-calibrate the system for a particular deployment on a particular day or a particular drive also, and make it work, right? The second is, again, for cost reasons, there is the ideal sensor. You might want to use a LiDAR for ranging, or you might want to use automotive radar and so on. Those are expensive. We want to be able to make do with the sensors that we have that are cheaply available, and do this essentially enable what we call a sensor substitution. Can we use a lower cost sensor to still do a reasonably effective job? And I'll talk about that as well. And the third thing is that if you think of IoT, the typical model is that there's a lot of data being generated, everything goes to the cloud, and your intelligence sits in the cloud. But obviously with imagery and video, you don't want to do that, and maybe you can't do that for a couple of reasons. One is just too much data, too much bandwidth required. Plus there's also privacy. You don't want to ship all the raw video to the cloud and look at it there. You may want to just detect events of interest at the edge, except that your edge device is now a smartphone, and it's not your iPhone X or iPhone 10 or whatever, right? It's a maybe $100, $150 Android smartphone, which has capability, but it's not leading edge by any stretch. So we need to be smart about how we do the processing at the edge device. So let me talk about each of these in particular context. Auto calibration applies to lots of aspects of our system, but I will just talk about one. So one thing that we have focused on a lot is gaze tracking, right? Because obviously where a driver looks is important from several viewpoints. And what we're showing in this video is that we're classifying the driver's gaze as one of 3: looking straight, looking to the right or left, where right, we hope, means looking at the right mirror and knowing what's behind them on that side, and then likewise on the left. Now, the way we do it is, again, we are not computer vision people, but there's a lot of literature on how you model a face, and there is this facial landmark model that people have, where for a human face, you could have typically like a 68 landmark model that identifies the eyes, the nose, and the mouth, and so on. And based on, if you take an image of a face and identify the landmarks, you can back calculate the pose of the face. You know which way the head is turned. Now, one thing we do is that we identify a subset of about 22 landmarks out of the 68 that is good enough for our purpose, and that allows us to run a slightly cheaper landmark extraction model, about 35% cheaper, so that's good. But there are a bunch of challenges. The first is that the typical setting where this kind of face tracking is being done is, think of a web conferencing setting. You're in front of a computer, you're doing a conferencing, you're sort of occasionally moving your head and so on. Whereas in the driving setting, you have frequent movement, and there's a combination of head movement and eye movement that you have to worry about, and I'll talk about that. The second is the camera is placed in what I would call as a non-standard position. It's not in front of the user, it's off to the side. If you place it in front of the user, we will cause an accident, right? So that's what we're trying to prevent. So it's off on the side, and also, as I said, it's variable. The mounting could change from one driving session to the next. And there is also driver and vehicle specific variation. As I said, a tall driver might sit back and therefore might turn their head in a different way than a short driver and so on. So what we do is, as a preliminary step, we take our raw data and we filter out the transient state. So when you're driving, there's a lot of head movement happening. We don't care about all of that. We want to know what are the dominant directions in which you're looking. right? And one would hope the dominant direction is the straight direction. That's where you should be mostly looking. But there are also the mirrors that you have to scan. So you repeatedly look towards those mirrors. So those are what we try to identify by taking the yaw time series and smoothing it and identifying these constant sections. Then the key step is where a driver is looking is not just based on which way they point their head, because people use a combination of turning their eyes one way or the other and turning their head. You may not even, your head may be held still, but you still roll your eye one way or the other to look at the mirror. So we have to incorporate that. And with the kind of cameras we have, the smartphone camera, we cannot get a precise angle for which way the eye is looking, because the number of pixels we have in the image is not good enough. So when you faced up with a hard problem that you can't solve otherwise, use machine learning. So basically what we do is we get the head pose angle using the facial landmark model, and then for the eye we just get an eye patch, essentially I think a patch of 120 by 80 pixels around where the eye is, and we train a network with a combination of the yaw and pitch angles and the eye patch. So the eye is not an angle, because what I mentioned, getting a precise angle is hard, and we use a relatively inexpensive convolutional network, a LANet, and we get a combined angle which tells you which way the driver is looking by combining both their head pose and their eye gaze, right? And then we use this for auto calibration. So when a drive starts, you look at the left here, we extract the direction the driver is looking, and then we identify these clusters. If you look at the chart on the right, by filtering out all these transient states, we identify the dominant clusters, and in this case there are 3 clusters corresponding to the driver looking straight. The driver looking right is actually shown on the left, and the left is shown on the right. And in India we drive with the driver sitting on the right side of the vehicle. So the right side mirror is close to where you are. So usually your pitch is more, you're looking more down, looking at that, whereas the left side mirror is further away, and so you have a large yaw is like your angle this way, so you're turning more to the left, but then your pitch is not that much. So that's kind of bears out in this data. So we identify these clusters automatically. So the assumption is that in the first few minutes of the drive, the driver would have shown the full range of movement. They would have, of course, looked straight, but also looked at their mirrors, maybe multiple times. And based on that, we identify these clusters, and that is very specific to that driver and that particular configuration and so on. Once we have done that, then for the rest of the drive, we can classify the gaze of the driver like I showed in that video earlier. So in fact, I'll go back to that in a couple of slides and do the classification. So I think this makes it clear. If you look at past approaches, so there was some work I think done out of Dartmouth about a few years ago, 5 years ago, where they did similar things except they used fixed thresholds. And we compared our approach with that and found that if you take a vehicle, put a tall driver versus a short driver and so on, fixed thresholds don't work very well. So you have to auto calibrate, and we are able to achieve reasonable accuracy, about 80 to 90% with our approach. So this is the same video that I showed earlier, except that now you see the landmarks and the tracking of the landmarks as things happen. Now one application of this is for tracking what's called mirror scanning, and this actually is not something we thought of. We actually talked to some external people, and they said, hey, when we train drivers, we train them to be situationally aware. They should obviously look straight ahead, but they should also know what's around them, and so they should scan their mirrors. So this guy, for example, I don't know if you can see from the color, for several seconds now, he has not looked this way or that way. He's just looking straight, and that's not good. And at some point in this video, I guess it will turn red and so on, and the moment he, now 20 seconds is too long. Actually 20 seconds is too long. You probably want to scan once every 8 or 10 seconds anyway. And at some point he will look this way or that way, and then he looked to the right, and then it got reset, right? So this is a very simple application of gaze tracking, and that's something that actually led us to work with the external partner, Maruti Suzuki. So if you're not familiar, Maruti Suzuki is the largest car manufacturer in India. So they make about 1.2 or 1.5 million cars a year, and they set up these institutes for driver training about 20 years ago, where they try to mostly for commercial drivers, sort of try to train them on good driving practice and so on. And they have actually trained about 3 million drivers over the past 20 years. And their setup, it looks like this. Oh, sorry. Why is the video not playing? Yeah. So they have these driving tracks that have all these mocked up streets and signals and so on. And the guy on the left here is the trainee. The guy on the right is the instructor who's supposed to be paying attention and looking at what this guy is doing. It's not very easy. He's quite distracted himself. But he's doing this, and then at the end of the drive, or end of the training session, I guess, he's supposed to fill out a form like this that rates the driver and points out to what he's doing right and wrong. As you can imagine, and there is a bunch of things. Yeah, I just called out a few. Like these have to do with the observations that the driver made. Did the driver look at the mirrors before making a turn and so on? Those have to do with speed and so on. It's hard for the instructor to be watching this guy. It's tedious. Plus, you're sitting by the side of the driver, so you can't be looking that way, right? You don't really know what the guy is looking. The second thing is that, if you were only trained here, then I think you'd be fit only to drive in a parking lot in California or something, right? The streets in India don't look like this. So you have to go out on the road, and out on the road, you don't have any of this infrastructure. So in the IDTR infrastructure, they have cameras on tall poles looking down, they have other sensors and so on. You won't have any of that. So you have to carry your sensor package with you, and a smartphone is a pretty good setup. So that's why they were quite interested in what we had. And as a first step, the goal is really to automate this entire form, or as much of this form as possible, so that a license test, I guess, would be administered by a device. Yeah.
How do you decide if you do a good enough job?
For this?
Let's say.
Yeah. So I will actually, the next slide kind of answers that. I mean, I don't have a direct answer, but so the thing we have started with is the mirror scanning part. Okay. And so what we did is we deployed, I don't know how many devices, I think 10 or so devices there, and across a bunch of training sessions, we generated events. We generated video clips of events that we think were of interest, like cases where the driver did not do the right thing with regard to scanning. Okay, and those video clips were then rated by the instructors as on a 5-point scale, and that's the chart at the bottom right there, right? So the instructor was telling us, was our video clip telling them something useful, where yes, the driver did something bad and we didn't even notice and it was useful, or we got it completely wrong, right? And so if you look at that chart there, we actually did two versions. The first version we did in the dark blue was our first version where we only used head pose to figure out which way the driver is looking, right? And then the second version combined that with the eye state. And I would say with the second version, especially the 4 and 5 star rated videos are about 65 or 70%, right? So that's pretty reasonable. We do have a few that are poor. So I think one way of knowing whether we are doing well is actually to just work with the people on the ground and seeing whether they think what we are giving them is useful or not, right?
I'm going to, it's okay to just do a follow-up. I'm going to channel Carol from the previous talk this morning.
Yes.
And the assumption here is that the instructors know what the hell matters, and that the set of things that they've been asked to check actually correlates with driving outcomes. Another approach you could use this sensor package for is to go completely in the other direction and say, we're going to put this on cars with fielded drivers, and then we're going to look at the people who do get in crashes or near crashes and those who don't, and then try to extract empirically what things actually are correlated with people who end up in crashes.
Right. No, I think that's a good point, and we have thought about it. The challenge is, I would say, we have gathered 25,000 kilometers of data, but fortunately no accidents and no crashes, right? So getting labeled data is hard. It's hard. We need more crashes, right? So my point is that it's good we have not had any crashes, but in principle, what you're saying is absolutely true. If you could instrument the entire country, drivers, all the drivers in the country, and you get data across everyone, then yes, you will get enough data. But in any limited study, it's going to be pretty challenging to get that feedback.
Right.
Labels.
We don't know. I mean, I've always thought this about our own driver's education. We don't know if the sets of things that we evaluate, in fact, the sets of people we let drive and don't let drive, if that's actually making us safer or not. Like, literally, people just made up some stuff and they said, this seems to make sense.
Yeah, actually, I would say in a slightly different way. Maybe the stuff even makes sense if everyone does it. If you're the only guy following the rules and the rest are doing what they're doing, maybe you're less safe, right? Speed is a great example. If you stick to the speed limit and everyone else going 20 over. So I think these are great questions. We don't have a great way of doing what you're saying. I mean, I think if we can come up with some way of doing it at modest scales, right? Because we're not going to be able to do,
You need people to crash. You could just have us come over and start driving.
Bring your insurance along.
So a related question, since you're working with Maruti,
Yeah.
do they have telematic systems that record things like speed and so on? When there is a real crash, can you get any data out of them?
Well, okay, so the people we are working with are the Maruti IDTR, so that's the driver training program they have. Maruti, the company, I don't think, I mean, I think now maybe get some engine data and so on from some other vehicles because they have an app and all that, but I don't think they get as rich data as you would hope. And
These are
yeah.
not CAN data, they do not have the entire CAN data. Like one way would
Oh, they have that, yeah. So I didn't give the context. So I just talked about RP. So basically, when we went in, they already had these, in the driving tracks, these overhead cameras looking down on vehicles and so on. They also have an OBD sensor, but more than that, they've also, some things are not available with OBD, like for example, the turn indicator. So they've actually tapped into those wires. They put these magnetic induction sensors on the pedals, so when you press pedals, you can get that. So they've instrumented their car. What they don't have is a view of the driver, the state of the driver, and what the driver is seeing, right? And that's where we are coming in.
I think Ramesh was asking about for all the roadie cars out there.
Yeah. So for their cars in the field, yeah. So they don't have the kind of data that you would hope to. Yeah. But I think it's a good point. I guess the way we are looking at it is our first step is, can we automate what's done manually today for two reasons. One is the manual part is not done well. The second thing is you can just clean up the process. Yeah.
But how do you know that the drivers aren't driving better because they're being recorded?
Oh, actually, they could very well be, and that's perfectly fine. And if you put a dummy camera in front of them and that makes them safer, we are very happy, right? I mean, so our goal is not.
They can't do it.
They can't prove that.
Yeah. So our goal is not to say that we have not modified behavior. Our goal is to monitor whatever behavior they exhibit while our system is in operation. If they exhibit great behavior, all power to them, right? We don't care.
You don't need to actually record anything.
I'm sorry?
You just have it on.
I know, yeah. Just have a blinking LED. Just have a blinking LED, like all the dummy security cameras they have, right? I think, yeah. So I think this is a good question, but it's a little orthogonal to our goal. As another example of something on the road, I mean, this is not with Maruti, but this is just in one of our drives. I mean, just to, this is a real. Actually, the postdoc Akshay, he went on a drive for a different project, 4-hour drive on some highways, and he noticed the driver was quite sleepy. But he didn't stop him because I guess he was on this project and he wanted to get data. I don't know what. He just kept going. And we analyzed the data, and if you look at eye closure, which is considered one of the best measures of drowsiness, it actually shows up. The first 40 minutes, the percentage of eye closure is largely under 20%. I think anything under 30% is considered good. And then further into the drive, I think an hour and to 100 minutes into the drive, the distribution shifts markedly to the right. So I guess this is just evidence that even simple devices and simple measures actually can provide you a pretty good indication. Now there's a larger question of what you do in such a setting, and that's why we decided to start with driver training, because that's a very confined setting where we don't have to deal with more complex issues. Like if you're a truck driver and you're found to be sleepy, maybe the fleet operator wants to stop you there, or maybe they care more about the delivery you're going to do, and they're willing to take a chance. We don't know. That all depends on other economics. Okay, so that was an illustration of auto calibration and the deployment we did. Now let me talk about sensor substitution. And this again shows up in multiple ways, but let me talk about one particular one. I talked about using face tracking and facial landmarks as a way of figuring out not just which way the driver is looking, but also things like yawning and eye closure come from this, right? Now the challenge though is that a lot of safety issues happen in low light conditions, nighttime and so on. And although you have some amount of street lights that allow you to see something, it's kind of poor. And in fact, we tried a lot of existing face detection things, even the face can't be detected, leave alone getting landmarks. So the question is, how do we monitor the driver state in low light conditions without requiring additional sensors? And so this is the goal. We want this low light picture to then give us facial landmarks based on which then we can do our detection. So the first step is, okay, we will introduce an additional sensor, a thermal camera, an FLIR camera that gives us a thermal image, and using that thermal image, and I'll talk about this in a couple of slides, we can build a thermal facial landmark model, right? So that given a thermal image, we can figure out where the landmarks are.
It's like a 320 by 200 kind of. I mean,
Yeah, it's
low res.
it's low res, yeah. And then the second step is with just an RGB image from a smartphone, no FLIR sensor, we train a model to synthesize a thermal image based on the low light RGB, right? And once you've done that, you can then feed the output of the second step to the first step and get the landmark. So essentially, you start with a low light RGB, and then you end up with facial landmark, right? That's the high level picture. Yeah, so basically, yeah, so I just spoke to this. So in testing phase, you have low light RGB, you synthesize a thermal image, and then you get landmarks out of that. And then you can run your detectors. Now, yeah.
Why is this the procedure? Why are you trying to synthesize a thermal image? I'm just trying to understand why you just aren't training it to recognize the landmarks.
Yes, we could. So there are two questions. So what, the reason we use thermal is that the good thing about thermal is that the thermal image is largely the same whether it's good lighting conditions or poor lighting conditions.
Totally got the
Right.
thermal
Yeah,
one.
yeah.
I don't understand the other one.
Why don't you train directly to get landmarks? We could. So I think the reason we did it this way is that we believe the thermal image that we generate is an intermediate representation that could be used perhaps for other purposes than just getting landmarks. So it's a sort of an informative representation of the scene that we could use, and we have not done that yet, but we just sort of did that in the hope that in the future we might find it useful. But I agree with you that you could directly train.
So I have a hypothesis, and I'd
Yes.
love to see what happens, which is that what's actually going on is that the image sensor that you have is picking up near IR, because most of them do. And that what effectively you are doing is training your thing to not use most of the visible spectrum. And if you just filtered off that other thing, you might be fine.
You mean just looked at the near IR part of the signal?
Portion of what's coming out of your image sensor.
It's possible, yeah. I mean, as I'll show in a couple of slides. I mean, obviously we're not. If there is absolutely, if it's pitch dark, we get nothing. So I'll show that. So I don't know what that says with regard to your hypothesis, but when it's pitch dark, when the illuminance value is 0 or close to 0, our synthesis obviously does nothing. So we can't generate image or nothing. I thought your question was, why do we have this intermediate step of thermal? And I think that's just because we want it to be available if you want to do things beyond landmarks. It's not just tied to landmarks.
Well, I assume that you're doing it is that allows you to generate a larger training.
No. So yeah. So that is true. But even with this, you could then train. Actually, let me complete this, and I think it'll be clear, right? So I think the key point is that the thermal image looks the same whether it's daytime or nighttime, whether it's good lighting conditions or poor lighting conditions. Now, the existing facial landmark models only work on good light RGB. Poor light RGB, nothing works, right? So we get in good lighting conditions, we can get RGB images and aligned thermal images. From the RGB image, we can get the face and we can get the facial landmarks, and we can just overlay that on the thermal image, and we can train a landmark model on the thermal images, right? Now, yeah, so we have that model. So now at nighttime, let's say you actually had a thermal image, let's say from the actual sensor. Now that you've trained a model, since the thermal image looks the same whether it's nighttime or daytime, we can use the same model to extract the face and the facial landmarks, right? So that's the reason to use the thermal sensor in the first place, because if you look at existing training data sets for face and so on, there's no low light data sets, right? And we can't be gathering and labeling manually a lot of data. So the thermal sensor with existing models gives us a shortcut to get a lot of labeled data at scale. Now, what you have in our setting is just the low light RGB. We don't have the thermal. So we basically, yeah. So anyway, I'm going to skip this part. Yeah. So then we need to synthesize thermal images, and for that we use what's called a GAN, or generative adversarial network, which is a relatively recent idea in the deep learning and machine learning community, which allows you to build. Actually, let me. Yeah. So basically, you have a pair of a generator and a discriminator network, which are being trained simultaneously. So the goal of the generator is to, if you look at the right side of the figure, given input RGB image, it generates or synthesizes a thermal image. And the discriminator has been trained with real pairs of low light RGB and corresponding thermal images. And so it knows, given this, or the hope is it knows that given a particular low light RGB, what the thermal image should look like. So if the generator does a poor job of synthesizing the thermal image, the discriminator can tell that that's fake versus real. And so, you know, this is, I mean, again, GAN is standard stuff now, and you should look it up. But essentially, that framework allows us to train our thermal image synthesizer using low light RGB. And here are some examples. In fact, in this picture, can you guess which one is the synthesized thermal and which one is the real thermal? Yeah, only two guesses, so I guess two hands. You should guess. Middle synthesizer, yes, exactly. Yeah. So if you look at the edge of the window and so on, it's actually not come out very well there, whereas the right one is good. Yeah. So so now this, I think, Stefan, maybe is somewhat related to your point. So if you have very little light, 4 lux, I guess, of illuminance, what we synthesize, the middle picture in the top row, is very poor. Obviously, we don't really have any signal to work with. Whereas as you move down the scale, things get better. Right?
Actually, you do shockingly well.
I'm sorry?
How little light you have, which suggests that just what you are showing there is a visual artifact. It looks black to us, but clearly there's something, because there's a head. Maybe not, you can't.
Right. No, but the thing is this. Think about it this way, right? You know, most people have faces with a certain geometric configuration. So even if you just know where my chin is or something, right? You can make a reasonable guess of where my eyes are.
No, but what it suggests is that you could do quite well just by having a little light on your sensor.
On our sensor?
Yeah.
To illuminate the driver's face?
Yeah.
That's true, but
especially outside of the visible range, so it wouldn't bother them.
Oh, I see. So that's where your near IR thing comes.
Right? Why not use just the IR camera? Yeah.
I'm sorry?
Is there an IR camera?
No, there isn't. So,
and it's expensive. Where is expensive?
This is expensive. Yes. But I don't know. Near IR shows. That's a good idea. We should think about that. What was the point I was going to make? I think I said it already. Yeah. So no, IR camera. So FLIR is an IR camera, and that costs a few $100s. So that's not something we can deploy at scale.
I see that a cheap IR, I guess, ones which are already on these current phones.
Yeah, but we are talking about $100, $150 Android devices. They don't have, at least today, have those sensors. In a few years they might have those sensors, in which case we may not need this, but we'll still use the IR part. Yeah.
So the idea is that he's going back to is that imagine instead of using the infrared, what you did is you simply got a camera with a larger aperture.
Yes.
So that's actually working with the light. And
Okay.
So then the model that it's trying to model is actually more directly mapping between the two. So you get a camera which can see totally fine with the ambient light that's available, and then the mapping isn't as abstract as it is between the ambient.
Right. No, I think, as I said, I think there are two questions here. I think Stefan's question is, during the synthesis, we don't need this intermediate step of synthesizing the thermal image. We could directly train for the landmarks. That's right. But I think during the training, it's still useful to capture these thermal images, because I think they're much more informative than what your near IR or larger aperture thing would give you. There's just more signal here, right? Because the thermal camera.
You can get it so it looks as bright as day with a high aperture. What I'm saying is you can get a camera which literally looks like you have a bright light.
Yeah,
I
but
see.
it's
I
just
see.
another special camera. Look,
Sure.
you realize, so CMOS actually can see much of this. They usually put a filter in front of it so that it doesn't block, it doesn't mess with what
Right.
you're normally doing. But again, it's a specialty device.
Sure.
And he's trying to have cost low. So.
Yeah.
One thought is that why not have glasses with rim fitted with the IR emitting devices, right? And these IR can be caught up
Where
by
did that
cameras.
idea come from?
No, I mean, yeah, so all those are fine. Again, we cannot deploy those at scale. And I should mention that for all what we have done, we don't really get the state of the eye very well with this model. We can get the head pose and we can get the mouth and so on, but we cannot get so we can't tell eyes closed, shut, open or shut very well with this so far.
What about during bright daytime conditions when people are wearing dark glasses?
That Yeah, so we haven't really, I mean, in some of these cases we will not have part of the signal, so we will not know. Actually, from a driver's viewpoint, we might ding them. I mean, they might have actually looked at the mirror, but since we couldn't see their eyes, we'll say, hey, you don't move your head, therefore your eyes didn't move. So, yeah, there are clearly blind spots to what we're doing. It's not, yeah.
So, are you doing this per frame? Because I imagine like 20 frames later or something, you might have a little bit more light. I mean, like the fact that it's a video.
Yeah, this is a good point. Actually, okay, I don't want to skip back, but that's okay. Maybe let me show you. That's why in this chart here, I talked about instance level and frame level accuracy, right? So, oh, sorry, I shouldn't have done this. This one. So we have accuracy at the frame level, and instance level is what you're saying. Essentially, we took 10 frames and look at the majority or something. So that way, even if some frames you got nothing, if the rest of the frames told you one thing, then you're good, right? So you're right. We don't have to, again, in a system like this, you have to live with the fact that there will be noise, there will be missing data and so on. We cannot expect every frame to give you things. So anyway, so where were we? So we were somewhere here. Yeah, so we have this GAN, and then these are examples, yeah, right. So with a system like this, about 7 hours of nighttime data, with a regular smartphone camera with the RGB images, we were able to detect landmarks in only 26% of the frames. With an FLIR sensor, we were able to do what, 90 or so percent, and with our technique, we are able to do 81%. So we do get much better coverage than with just RGB, and we then ran detectors on this. So for yawn detection as well as mirror scanning detection, and again the accuracy is the 70s or 70s, 80%, right? Not perfect, but reasonable. Yeah.
What is the latency of
the GAN? You're talking about for this one? Yeah. So this one is actually very slow. So this is not running on the phone just yet, because I think yeah, the GAN model is quite expensive. So that's something we need to work on. Yeah.
First of all, this made me remember that I guess I didn't see a lot of people driving with sunglasses in India. It's super popular in America, but it's not really popular in India. It's kind of funny. When you saw the picture of the training course, the first thing I noticed was the generous lack of cows on this, like normal things you would see in India. And I was wondering if maybe then what you're doing here is actually leading towards an obvious next thing, which would be to follow the person's gaze and follow what's outside. And say, oh, here comes this thing. Is the person actually looking at it? If they're not,
Yes, actually, one of our academic collaborators actually is a computer vision group in IIIT Hyderabad, and they are interested in doing exactly this. You have the gaze, and you have the outside camera. Can you figure out what they were looking at?
Because to me,
right?
That's the worst part of India. It's like something comes out of nowhere, and like if you're not paying attention to it, then you have microseconds to deal with.
Yeah, I drive in both places. I actually find it less stressful there. You may find it hard to believe, because speeds are low, and when in doubt, you can stop. Right? I'm sorry? Yeah. No, I think. Yeah. But I think this is a good point, and this is something that it's a work in progress. I mean, the university group is driving it, and hopefully they will have something soon. So let me get to the last technical part. So this is about how do we do all this processing on a smartphone-like device, and I will do this in the context of a particular problem, which is vehicle ranging. Right? So figuring out how far you are from the vehicle in front. Again, this is a very basic task from a safety viewpoint. There is the so-called 2-second rule, which in our data we found no one in India follows. Like 2 second. Problem with 2-second rule, then your 2 seconds will get divided. Someone will slip in between, and then you won't have that separation. But the idea is you're supposed to keep a separation that's at least 2 seconds worth of distance you're traveling at your current speed. Right? That's what's recommended. And obviously there are sensors like LiDAR you could use for ranging, but they are expensive. And also the other aspect we worry about is the heterogeneity of vehicles and the fact that the vehicles are not in nicely marked lanes. Right? Even if lanes are marked, the vehicle might be straddling lanes and so on. Right? So there's things you have to worry about. Now, in recent years, DNNs have proved to be great at object detection kind of tasks, and vehicle detection and so on is object detection. So in a nutshell, our ranging idea with the camera is very simple. Once you find a vehicle, you draw a box around it. The size of that box, along with the known size of that vehicle, tells you how far it is. Right? It's simple trigonometry. The problem, though, is that the state-of-the-art techniques for detecting these vehicles and objects and so on based on DNNs are quite slow, right? It could take hundreds of milliseconds to run on a smartphone CPU. Now, the approach we take is this hybrid of combining DNN-based detection done infrequently with much cheaper computer vision tracking. So the intuition is very simple. If the vehicle is in front of you, it's not going to disappear the next moment, right? It will likely be somewhere in the same vicinity, so you can actually track it. And this is, well known in the computer vision community, the tracking algorithm. So we just combine it in a way that actually works for our problem. So, to me, it's a bit reminiscent of MPEG coding. You have your iframes, the expensive frames, and then the rest are delta encoded with respect to the iframe, except that we do this adaptively. It's not that every 15 frames we are going to do a detection. That's wasteful and sometimes inadequate. You have to look at, did the scene change, some new vehicle, let's say, shows up in front of you, then you want to do detection again. On the other hand, if you're following a vehicle for a while, you can continue just tracking it, right? And just as an example, on average, in some of our traces, we find that we have to do detection once every 15 frames, but that's on average. Sometimes it will be more frequent, sometimes less frequent. But that allows us to go from 2 frames per second to 15 or 20 frames per second, right, which is a significant improvement. So that's what we do, along with a few other things. We also do what we call as region of interest filtering. So if you're driving, even though there are no lanes, from a ranging viewpoint, really care about what's in front of you. I mean, you could be 2 feet away from the vehicle to your side, and that doesn't really matter. Also, we need to identify the type of vehicle, because the bounding box size has to be combined with some knowledge of how large the vehicle was to begin with. And when you're talking about heterogeneous vehicles, two-wheelers all the way to trucks, we're talking about a fairly wide range, right? So we need to identify the vehicle. So we do that, and this just shows, we have the frame, we identify the region of interest, which for convenience I've not shown in the remaining frames, but once you've done that, you ignore everything outside of it, and then you detect the vehicle in frame 0, and then you track the same vehicle 10 frames later, right? And this is the system in operation on a street in Bangalore. This is a somewhat controlled setting. We have one of our vehicles going in front, and we've asked the guy to go faster, slower, and so and occasionally we latch onto a different vehicle, and so on, right? Now we actually did experiments, and we thought, LiDAR would be great for ground truth, except we found that if you just have a LiDAR, and we actually have 4 LiDAR units, these LiDAR Lite 3 things, fairly inexpensive, $150 ones. You will get a range value, but you have no idea what it bounced off of, right? So you can point your LiDAR, and let's say a two-wheeler comes in front of you. You don't know whether it's bouncing off the two-wheeler or the vehicle in front. So you get a very precise measurement of something that you don't quite know what it is, right? So the LiDAR curve has these spikes that I think correspond to the laser beam just hitting something at a distance every so often. But if you look at the orange curve, which is our scheme, and the LiDAR part, they're quite in agreement in this case. Ion Road is actually a smartphone app from some Israeli company that also does ranging. We don't quite know how it does it, although we have some guesses, and I'll get to that in a couple of slides. And all 3 are in reasonable agreement here, except for this few spikes. This is a different segment of the drive where actually Ion Road produce a much higher range than us. And what's happening here, you can see here, right? So this is our technique HAMS on the left and Ion Road on the right. So what we believe Ion Road is doing is, whether there is lanes or not, it imagines a lane, right? And it looks at how much of that lane is being occupied by that vehicle, right? So that's one thing it's doing. The second thing is that it can't detect the two-wheelers and the three-wheelers and so on. It latches onto some vehicle that it knows about at a greater distance. So in a lot of situations, it produces a range that is significantly higher than us, because the two-wheeler, for example, here, our bounding box has picked out the two-wheeler, that one is looking past the two-wheeler, right? So this speaks to sort of the fact that we have heterogeneous traffic and there's no lane. So, okay, here there are some lane markings, but the point is that even if there are lane markings, it may not be a standard width lane, right? So you have to worry about that. So in general, I think depending on infrastructure support, even if the infrastructure is minimal, is not a good idea. It will be good to make the system robust to such variations. So that's our thing in operation. And this is data from I think some developed country. KITTI is a computer vision data set repository, and so they have data from either the US or Europe or something. And what we're showing is the ground truth distance, and they have a fairly fancy, not our puny LiDAR, they have a Velodyne LiDAR setup, so they have real ground truth, and our estimated range on the y-axis, and we are pretty much along the diagonal, so we're doing reasonably well. And then in terms of ranging distance, we have a bunch of techniques, which in the interest of time I will skip, where we can range, the blue bars stop at around 30 or 40 meters, whereas we can range at distance of 80, 90 meters by doing some augmentation while we train our networks and so on. And here are a couple of examples of vehicles we think are at 98 meters. We don't know because our LiDAR can't be aimed at those, but they seem pretty far. So I think the smell test passes, I guess, in this case. So okay, so with that I will conclude. What I've talked about is a low-cost solution for monitoring drivers and their driving, and a lot of our technical work arose from the fact that we have to make this thing work on the edge device and make it robust to things like variation in the orientation of the camera, the sitting of the driver, low light conditions, and so on. We gathered a bunch of data in MSR India, most to sort of get a feel for this. We have 25,000 kilometers of data, but the problem now is that none of it is labeled. So it's a pain to even label it. So we have actually worked with a fairly small set. It's a big number to throw out. It looks impressive, so I put it there. But we have worked with about 600 odd kilometers that we have labeled. We are working with this external partner on driver training, and I think the same technology could be deployed in multiple ways. When we're looking at driver training now, you could think of automatic licensing, or in a fleet setting where you are the owner of 100 trucks or 1,000 cabs, you can see how your drivers are doing and sort of keep tabs on them in the setting. And I really think that automated monitoring is key to safety. Even if the monitoring is just a blinking LED, so long as the driver knows that there is a feedback loop, and there is a feedback loop, I think it will make a big difference. So that's the end of my talk. I have one other slide just to talk about the lab, and if there are students interested in opportunities, I can talk about that. Let me just go through that. So, if you've not been to MSR India, you should talk to Jeff, who was there 10 years ago, or Aaron, who was there 9 years ago, or Rajdeep, who was there more recently. I don't know where Rajdeep is, somewhere in the audience, I think. And yeah, there, yeah. So, I don't know exact count because we've hired a bunch of people. So I think it's about 55 full-time people across pretty much all the areas of computer science, theory, systems, AI, ML, and what's called technology for emerging markets, which is a very interesting group of CS people combined with ethnographers and sociology people and so on. And we have lots of projects. I just called out some that might appeal to people with a systems background, machine learning on really constrained devices, a device with 2 kilobytes of RAM. Think of Arduino, Uno, whatever. Really, so I think there is some interesting work there. System support for DNNs, secure machine learning. So how do you do machine learning without actually learning about the data? And something that I'm working on with some folks in Redmond on data-driven networking. So essentially, a company like Microsoft or Google or Facebook, they have lots of services that are interacting, that have a visibility of performance between the cloud and clients out there. Can we leverage that volume of data to make better decisions for other applications and sort of essentially leverage all the data? So instead of a new TCP connection starting with a blank slate, you could use data. You could do better selection for relays in Skype, for example. We've done that. There's a bunch of opportunities, right? And so we actually have internships openings both in India as well as in Redmond for this. So if any students interested, please come find me. And recently, in the recent years, we have done extremely well in hiring. So we've hired some really great people, and even the postdocs we've hired are so good that we just turn them into regular employees. So the only thing that's missing in that list is UCSD. So we really would love to complete our hiring from top schools by getting someone from here. So I think the ball's in your court. Do come talk to us. Thank you.
We are a little bit over, but are there any remaining questions for Venkat?
Yeah.
So you suggest that cameras are the missing piece over.
I'm sorry?
Camera data is
Yeah.
the missing key over like GPS and accelerometers. And
Yeah.
so on.
Yeah.
But how would you combine those different data sets for experimental? Have you done that before?
Yeah, no, we are in the early stage of that. I mean, I spoke about an example of that, right? So let's say you detect sharp braking, which you would detect using an accelerometer or GPS. What you would do then is look at the camera information from a few seconds before and maybe a few seconds after to get more context. Was that sharp braking something that should have been anticipated, or was it unanticipated? Was the driver engaging in some behavior that perhaps led to that? So I think, just if you just blame someone for sharp braking without knowing the context, that might feel very unfair to them. If, on the other hand, if you had context, you might be able to do a much more nuanced job. So that's an example of a way of combining these.
All right, let's thank Venkat one last time.
Thank you.